Okay, good afternoon to everybody. First I present myself. I'm Carlo Boursier Niutta. I'm a postdoc researcher at the Department of Mechanical and Aerospace Engineering at Polytechnic di Torino. And today my talk is on the influence of additive manufacturing defects on the energy absorption capability of lattice structure. This is the outline of the presentation. I will first introduce the topic. I will talk about an extensive experimental campaign that we conducted on this lattice structure and that we used to validate the finite element model. Once we validated the finite element model, we wanted to investigate the effect of some additive manufacturing defects that I will describe later. So I will show you how we modeled the defects and their influence on the specific energy absorption of the lattice structure. And then in the end I will give you the conclusions and I will give a brief outlook on the future development. So for those who are not familiar with the topic, lattice structures are three-dimensional structures that are composed of repeating unit cells. And the recent advancement in the 3D printing has allowed the increasing use of these structures. So we started investigating the energy absorption capability of different several lattice structures. And among them, we identified this one as the best performing in terms of energy absorption. In particular, this one was made of carbon nylon from carbon nylon filament and produced with fused deposition modeling. Then we performed a more extensive experimental campaign on this lattice structure. And in particular, we performed two factorial plans. In the first one, we investigated the effect of two geometrical parameters, the diameter d and the size of the unit cell, the length L. In particular, according to the factorial plan, increasing the level, we added the size of the L decreases. And in the second factorial plan, instead we investigated the effect of the number of cells that we consider in a specimen. And so we kept the size of the unit cell constant, L constant, and we varied the number of the cells considering different replications of the cells, so 2 by 2, 3 by 3, or 4 by 4 replications. There were some specimens that we produced. So after the production of the specimen, we conducted the compressive test in a static manner. And there you can see also how we calculated the force displacement, the energy absorption from the force displacement curve. In particular, right after the peak force, we integrated the force displacement curve in order to obtain the energy. And this integration was performed until the densification occurred in the test. Indeed, the tests were ended when densification occurred or when the 60% of the specimen weight was reached. Here you can see the main results of this experimental campaign. In particular, on the left you can see the results of the first factorial plan, where you can appreciate that there is an influence of both the diameter and of the length size of the unit cell, and also that you can see that the larger the cell density, the larger is the efficiency in absorbing the energy. Indeed, the larger is the diameter and the smaller is the length of the unit cell, the larger is the efficiency in absorbing the energy. Instead, here in the figure on the right, we have the results of the second factorial plan, where again it can be appreciated that the specific energy absorption increases with the diameter of the beams. And also that the number of cells does not influence the specific energy absorption, which is a really important result because it means that we can evaluate the specific energy absorption of a unit cell on a specimen made of small replication of the unit cell, and then we can use this result in the design of a component that is made of several replications of the unit cell. Then we use these results, these experimental results, to validate a finite element model that we constructed in LS Dyna. For the finite element model, we decided to use 1D elements, one-dimensional elements, And this choice was mainly due to computational effort that is consistently reduced if you use 1D elements instead of 3D elements. However, with the 3D elements, you can take into account the geometrical variations that can occur during the manufacturing process. However, the consistent reduction of the computational time is something that we were looking for in the aim of designing also components with lattice structures. And from the material point of view, we selected an elastoplastic material law, that is the material 24 in the design. Here I reported the material properties, density, Young's modulus, and yield limit. And for the plastic field, we conducted some tensile tests on specimen realized with the same material and with the same process parameters. So from that we extracted the plastic field, the stress strain curve in the plastic field. So here is the validation of the finite element model. I'm sorry that the green line here is not very visible. Anyway, the comparison between the two. Here on the left we have a case of the second factorial plan with the diameter of 1.1 millimeter and 3 replication of the cell. And you can see that the finite element model is able to capture the progressive crashing behavior of this structure, which also results in a force displacement curve that is characterized by these peaks and valleys. And these are mainly due to the fact that each layer of cells progressively crash. While here on the right, you have a comparison for a lattice structure of the first factorial plan with a diameter of 1.8 millimeter and this length 6.38. That was actually the most dense structure that we investigated. And you can see that in this case the failure crashing behavior is completely different. It is a foam-like crashing behavior. And even in this case, the numerical model is able to capture, well capture the failure and the crashing behavior of the structure. So once we validated the finite element model, we decided to investigate the effects of some additive manufacturing defects. And in particular, we considered two defects. The first one is a variation of the diameter, and we consider a 50% of reduction with respect to a nominal value of 1.5 millimeter. This was mainly due to the fact that during some optical observations that we made on the specimen that we produced, we were able to see that there were consistent variation of the diameter from the nominal value that we selected. And the second one, defect that we consider is the lack of fusion. Instead of modeling it as a discontinuity within the beam, we decided to use this material mat null in LS-DYNAM. That is a material that prevents the transferring of the loads from one node to another. And so through this material, the energy absorbed by these elements that are the defects one is null. Also, we consider different percentages of defectivity by inserting different numbers of defective beams within the unit cell. Then for the construction of the specimen, we just replicated the unit cell with defects, and then we performed the simulation. And also, to investigate the effect of the location of the defects within the unit cell, we considered 3 different cases for each percentage of defectivity by randomly distributing the defects within the unit cell and then replicating and simulating. So in total we performed 12 simulations for each kind of defect that you consider. And here you can see the results of this numerical analysis, where you can see that we have a consistent reduction of the specific energy absorption with the increase of the defectivity. Also, you can appreciate that there is a consistent variation of the confidence interval from the analysis that we make with the random distribution of the defects. And you can see that the confidence interval tends to increase for a middle range of defectivity, while it is a bit lower at the extremity of the domain. And this can be explained by the fact that the location of the defects is also an important factor. Indeed, when we have a small percentage of defects, the pristine material can compensate the presence of the defects, and so the location is not anymore an important factor. And similarly, when we are in this other extreme, we have that the defects are dominant over the pristine material, and so the location is no more important. While in the middle range, the location of the defects is an important factor. And similar considerations can be done for the lack of fusion defect. Again, there is a consistent variation of the specific energy absorption with the defectivity. In this case, it was a bit more severe with respect to what we obtained with the variation of the diameter, mainly because we modeled the lack of fusion as a material that cannot absorb any energy. And also similar consideration can be done on the confidence interval, which tends to decrease for the middle range of the defectivity. In this case, it decreases a bit more faster because of the major severity of this defect. So in conclusion, the experimental campaign has shown that the larger is the cell density, the larger the specific energy absorption, and also that the number of cells does not significantly affect the specific energy absorption, which means that we can test specimen, we can evaluate the specific energy absorption of a unit cell on specimen made of small replication, and then use that result in the design of a component. And also, we have seen that the presence of the defects from the numerical analysis consistently affect the specific energy absorption of the structure, and that the location is also another important parameter. So in the future, we intend to correlate the microstructure to the mechanical performance that they are obtaining in order to obtain a sort of design curves, the type of that I've shown you before, so the specific energy absorption as a function of the defectivity. And also through these design curves, we can make a component validation once the microstructure has been characterized. So with this, I conclude my presentation, and I thank you for the attention.
Okay, questions? Yes, please.
Thank you for your presentation. One question: how did you model the lack of fusion defects in your mechanical model?
Yeah, we, instead of this a simplified way, we started thinking that when you have a lack of fusion in these very small beams, you can assume that the beam is a sort of disconnected beam. This is a discontinuous beam, and instead of making the beam discontinuous, so duplicating the nodes, we decided to use this material, the mat null, that is going to work in the same way because it is not absorbing any energy, and if you have that the structure is discontinuous, the load will not transfer, and so it will not absorb any energy.
It's a broken beam.
Yeah, more or less the same. However, we did it with this material, and it works in the same way. We also verified that.
And you model this in an RVE fashion, and you use the effective properties on the core.
Yeah, we add the defects to the unit cell and then replicate it to the specimen.
It was explicit modeling of the core or with the effective properties?
What do you mean, sorry?
You made an homogeneous material within the skin.
Yeah. Yeah.
Okay. Thank you.
You're welcome. Thank you.
Okay, any more questions? If not, thank you very much.
Thank you.